Hello friends, welcome to the course Essentials of Data Science with R Software 2, where we are trying to understand the topics of sampling theory and linear regression analysis. In this module on linear regression analysis, we will consider the multiple linear regression analysis. So, you will recall that in the earlier lectures what we have done up to now, just a quick review. We consider the multiple linear regression model and we have obtained the ordinary least square estimators of the regression coefficient vector beta, right. And then we obtain the fitted model and then we obtain the residuals, and we also learned how to implement and how to obtain those values in the R software. Now, I will try to continue, and in this lecture I am going to concentrate on two aspects. First is this: whatever ordinary least square estimator we have obtained, I will try to state the properties of those estimator, and then I will try to come to the aspect of maximum likelihood estimation. So, the first question comes that why should I state you these properties, and then why only state, why not prove? The first thing is this: when you are trying to obtain a model from on the basis of some small set of data, and this model is going to be valid for a very big population. So, the question is this: you have to be confident the way you are obtaining the model is good or bad, number one. Ultimately, whatever is the definition of statistical modeling, for us now it is a very simple thing, we have to estimate the parameters. So, now the question is this: there are different types of estimation methods for estimating the parameters. Now, I would like to know that whatever values I am estimating for my parameters on the basis of random sample of data, are they giving us a good value or not? Now, once I come on the aspect of good, then this good is defined with respect to the statistical properties. Now, the question is this: I expect from you that you have a reasonable background in statistics, but there may be some audience, some students, some faculty who have not done a course on statistical inference like what we do in the undergraduate or say postgraduate courses in statistics. So, giving the proof to them will possibly make their life difficult, but as a user I believe that they must know that what are the different properties, and you have to believe on me that if you want, you can go to the books and look at the proofs of those results. But this will give them a confidence that whatever I am doing, that is correct. And moreover, when I come to the field of data sciences, many people are now venturing into this area. People from computer science, people from different types of subject, they are coming, they are trying to learn this data sciences. It is not only those people who have done a full course on statistical inference, they are doing or they want to become only the data scientists. So, keeping in mind all these factors, what I have done, I have just comprehended all the results so that you can be confident. Wherever the results are simple to prove, there I am trying to do it, and rest I would leave it up to you that how much you want to learn in the theory. I will try to give you the sufficient concept with sufficient theory, and after that I will try to show you how to conduct the maximum likelihood estimation in the framework of multiple linear regression model. Right. Okay. So, let us now begin our lecture. Okay. So, now you can recall that our model was y equal to x beta plus epsilon. This is our multiple linear regression model, where y is a n cross 1 vector of observation on steady variable, x is a n cross k matrix of observations on k, independent or explanatory variable, beta is a k cross 1 vector of regression parameters, and epsilon is an n cross 1 vector of random error components. And based on that, we had employed the principle of least square, and we had obtained an estimator of beta hat, which was indicated by B, and this was x transpose x whole inverse x transpose y, and B is called as ordinary least square estimator, OLSE. Right. So now we are going to state the properties of this OLSE. So this OLSE is an unbiased estimator of beta. So the expected value of B is going to be beta. So some of these properties I will try to prove after stating it, but at this moment you can just take them as a result. And if you recall, in the case of simple linear regression model also we had proved this result. If you recall, in the case of simple linear regression model, we had obtained the variances of the least square estimators of slope parameter and intercept term estimators, and we had obtained their covariances also. So we had obtained the variances of B0 and B1, and we also obtained the covariance between B0 and B1. Now in this case, you have here B is equal to B1, B2 up to here Bk. There are k parameters. So for that, we try to obtain the covariance matrix, so which is defined here as say expected value of B minus beta into B minus beta transpose, and this is actually going to be a matrix here like this, where the diagonal elements are going to indicate the variances, and off diagonal elements are going to indicate the covariances. Right. So if I try to say, suppose I have here B is equal to B1, B2, then the covariance matrix of B, if I try to write covariance matrix of B, this is going to be something like this. On the diagonal elements, you will have variance of B1 and variance of B2, and off diagonal elements will be covariance between B1 and B2, and here also covariance between B2 and B1. So this is how we obtain the covariance matrix of an estimator. So the covariance matrix of ordinary least square estimator is given by sigma square times x transpose x whole inverse. So here also you can see that unless and until you make an assumption that rank of x is a full column rank, you cannot obtain this unique inverse, and hence you cannot obtain this variance covariance matrix. Right. So after this, we try to find an unbiased estimator of sigma square. This is obtained by this expression, and let sigma hat square hat indicates the estimator of sigma, which is given by 1 upon n minus k times y minus x b transpose y minus x b. And if you try to see, this term is simply your here y minus x b is E, so this become E transpose E divided by n minus k. Very simple to remember. Right. So this will give you the estimator of sigma square, and we are indicating this estimator of sigma square by small s square. And now if you try to look at this expression, try to see my pen in red color, this expression for covariance matrix of B. Right, here we have got the term sigma square. So now if you want to find out the value of covariance matrix of B on the basis of given sample of data, this sigma square is unknown, so we cannot find it out. So this creates a trouble. So now we have here a solution. The solution is this: now you have estimated sigma square by sigma square hat here, you try to put it here. Right. So once I try to do it, I can obtain an estimate of the covariance matrix of B like this, just by replacing sigma square by sigma square hat here times x transpose x whole inverse, and this expression will give me an estimate of the covariance matrix of ordinary least square estimator. So this is variance of B hat. So hat is indicating that this is an estimator. Okay. Now I come to another aspect. Up to now we were considering the properties of ordinary least square estimator B. Now you have obtained the fitted values, y hat is equal to x b. So you can now think, y hat is the value which is of very important for us, because if this value is close to y, then I can say my model is good, and if this value is very far away from the model, then I will certainly say that my model is not good. So, definitely this also depends on b. B is a statistics, a random variable. So, definitely you would like to study the properties of y hat also. For example, if this has got a very high variance, possibly you can say that the model is not well fitted, model is not good. So, that is why I am trying to write down these two expressions. So, first I try to find out the covariance matrix of y hat. Y hat, because if you remember, this will also be a vector like y1 hat, y2 hat, say yn hat. So, this will also be so its variance could be in the form of a covariance matrix. So, this covariance matrix variance of y hat is given by like this sigma square x transpose x whole inverse x transpose, and you can recall that this matrix here x transpose x whole inverse x transpose is your H hat matrix, which we have discussed earlier. Right. Now, again we have the same issue that this variance of y hat depends on the covariance matrix of y hat depends on sigma square, which is unknown to us. So, we try to estimate it by sigma square hat, and we try to replace it by here say s square or sigma square hat. So, then I can estimate the covariance matrix of y hat like this, which is sigma square hat into x transpose x whole inverse x transpose, and which is same as sigma square hat h. So, briefly I can write it down here, say s square h. Right. So, this will also help us in getting the further details of the model. Now, next we have a theorem which is very important for us, which is called as Gauss-Markov theorem. So, this theorem helps us in taking a final call that the ordinary least square estimator which you have obtained to get the values of the unknown parameters on the basis of given sample of data, are they good or bad. So, this theorem states that the ordinary least square estimator of beta, what you have obtained here, is the best linear unbiased estimator of beta. What does this mean? Suppose if I say, suppose there is an unknown parameter beta, and this can be suppose estimated by say some estimator beta hat. Now, somebody suggests a different estimation procedure, and the value of beta or the estimator of beta is obtained here as a beta tilde. Similarly, somebody suggests another estimator, and this estimator is say indicated by beta star and so on. Suppose there are so many estimators for estimating the same parameter, that can happen. Somebody may like to use arithmetic mean to estimate the population mean, somebody may use median or mode or harmonic mean, geometric mean to estimate the population mean. Right. So, now from these possible estimator, we can classify them into two groups: those estimators which are linear and those estimators which are non-linear. Remember one thing, I am not talking of the linear model or non-linear model, I am talking of the linearity of estimator. So, this means linear in y and non-linear in y. If you remember, we had expressed the estimator B1 in case of simple linear regression model as say summation k I y I. So, it was a linear function of y. Now, some of the estimators out of these possible estimator will come here, and some of the estimator will come in this group. Now, try to ignore this group. Now, there will be suppose some estimator beta hat 1, beta hat 2 and so on. Suppose there are a couple of estimators which are all are linear in y. Now, I try to impose here one more condition. I try to divide them into two groups. One group here is something like which is consisting of those estimator which are unbiased, and then means another groups those estimator which are biased for beta. Now, ignore those biased estimator and try to consider all those estimator which are here unbiased, and then try to find out the variance of each of the estimator here in this group. Now you will see, out of all possible estimator whatever you have considered here, this ordinary least square estimator will have the minimum variance among all. So that is why this is called as best linear unbiased estimator. Best is with respect to variance, and linear is linear with respect to y, and unbiased is that expected value of b is equal to beta. So that is why this is a very good estimator, and this Gauss-Markov theorem certifies it, that the values of beta which you are trying to obtain from b, they will give you a good value, right. Now after this I try to address on another property which is consistency. Consistency, I am not considering here the details, but in general I can say here that you can see here B is x transpose x whole inverse x transpose y, and this depends on here n. So who can say here this is a function of n k. So B is a function of here n, that is the sample size. And what are you trying to do? There is some unknown population here which has got the parameter vector beta, and you are trying to estimate this parameter by here Bn. So what I am trying to say here, that as n is going to infinity, this Bn will be converging towards beta. So the, in simple language I can say, if you try to increase the sample size, then this Bn will be converging to beta. And what we try to say here, if I try to translate it into a statistics part, means I can write in a much simple way. That let me try to write down here. Try to see the steps of my pen. So I have here a parameter beta, which I am trying to estimate by estimator Bn. So I want to see what is the difference between Bn and beta. So we expect that this difference should be as small as possible if my model is good. So I try to say here, this is suppose less than epsilon, where epsilon is some positive quantity, small quantity. Now I am trying to say this difference Bn minus beta can be positive or negative, but it does not make any difference for us. So we try to take here its absolute value. Now this is my event, that I want that Bn and beta should be close enough. That means I have to put some condition that what happens such that Bn is converging to beta. So what I say here, that let me try to compute the probability of such an event, that the difference between Bn and beta is as small as possible. And I am trying to say here, if you try to increase the sample size n, and I try to compute this probability as limit n tends to infinity, that means sample size is becoming larger and larger, then what do you expect? This probability should be equal to 1. That means the difference between Bn and beta becomes 0. Right. If this is happening, then you would say that Bn is a consistent estimator of beta. So in this case, I can just show you here, means I will not prove it, but I can inform you that both the ordinary least square estimator of beta as well as ordinary least square estimator of sigma square, both means B and S square, both are consistent estimator. B is a consistent estimator of beta and S square is a consistent estimator of sigma square, right. So this is actually called as convergence in probability, and this is indicated as Bn tending to beta in probability. And if you remember, when we had discussed the basic assumptions of multiple linear regression model, then the last two assumptions, that limit x transpose x upon n goes to some positive definite matrix delta as n goes to infinity, and this vector x transpose epsilon upon n as limit n goes to infinity goes to 0. These were the two assumptions we had made, and these two assumptions are made when I try to establish the consistency property of B and S square. Okay, so this is how I want to go. Similarly, there is another property in statistics which is called as Kramer-Rao lower bound. So Kramer-Rao lower bound gives us the value of the minimum variance which an estimator can achieve. That means the variance cannot go beyond that limit. So, well, there is a whole theorem. I am not explaining here the entire theorem, but if you try to use that theorem and if you try to find out the Kramer-Rao lower bound for the ordinary least square estimators of beta and sigma square, this will come out to be here like this. And means if you try to find out the covariance matrix of OLSEs of beta and sigma square, this will come out to be here like this, which is indicated as sigma OLS, right. So, you can see here that this value, I am trying to write down here in blue color, this and here this, they are the same. So, that means B is attaining the Kramer-Rao lower bound. This is the covariance matrix of B. So, this is and this is the Kramer-Rao lower bound of B. Both are actually same. So, you can see here covariance matrix of B and Kramer-Rao lower bound CRLB of B, they are the same. So, I can say that B attains the Kramer-Rao lower bound, or the Kramer-Rao lower bound is attained for the covariance of ordinary least square estimator B. So, you have a reason that B is going to give you a good value. But now, if you try to see the covariance matrix of sigma square hat, this is something like sigma square hat, right. This is here 2 sigma raised power of 4 divided by n minus k, and the Kramer-Rao lower bound for this sigma square hat is 2 sigma raised power of 4 divided by n. So, you can see that this covariance matrix of sigma square hat is not equal to the Kramer-Rao lower bound of say sigma square hat. So, S square does not attain the Kramer-Rao lower bound. So, that means, but you can see here that if n is becoming large, then there is not much difference. If you try to see, this is here n and this is here n minus k, but yeah, theoretically it is not attaining that, may reach as close as possible. So, that is why we always say that it is a better option if you have a larger data set. Now, if you ask me that what is large and what is small, that is a very difficult question, and that depends on the experiment, that what should be the optimum sample size, so that you get a good outcome. Right. Okay. After this, after stating all these properties, let me try to give you a quick proof, means the basic steps how one can obtain the proof. So, this will help you if you want to study further, then you can use a book and you will very easily understand it. So, whenever we are trying to prove that any estimator is biased or unbiased, what we try to do, suppose we have a parameter beta which is estimated by beta hat. So, we try to find out the difference. This is called as estimation error. And then what we try to do, we try to take its expectation. So, this will give us an idea about the bias of beta hat. And in case if you try to take the expectation of beta hat minus beta transpose beta hat minus beta, then this will give you an idea about the variance of beta hat. And if you try to consider expected value of beta hat minus beta into variance of beta hat minus beta, then this gives you an idea about the covariance of beta hat. This is the covariance matrix. Yeah, sometimes students get confused whether this prime should be on the second bracket or on the left bracket. Right. So, I can give you a very simple trick. You can just follow this rule. Variance is a scalar quantity and covariance matrix is a matrix quantity. So, once you are trying to take here the expectation sign here, you can see here beta hat is a vector of order k by 1 and here is the transpose. So, this vector will become 1 by k and the second vector is k by 1. So, the entire product will be of order 1 by 1. So, that is a scalar. So, when you want to find out the variance, then you try to put the transpose in the first bracket, on the first bracket. And once you are trying to consider this second quantity, so you can see here this is of order k by 1 and this is of order 1 by k. So, this is going to be of order k by k. So, this is going to be give you a matrix. So, when you want to find out the covariance matrix, then you try to put the transpose on the second bracket. I think there cannot be a better way to remember all these things. Right. Okay. So, first I try to find out here the estimation error of B. So, this is B minus beta. So, this is the expression for B minus beta, and here in place of here y, I try to substitute y equal to x beta plus epsilon, and if you try to open it, the first term will get cancelled out and you will get here x transpose x whole inverse x transpose epsilon. So, this is your estimation error. Now, since you have assumed that x is non-stochastic, this is constant, and you also have assumed that expected value of epsilon is 0. So, if you try to take the expectation of this quantity, you get here expected value of b minus beta, which can be written as this factor into expected value of epsilon, which is 0. So, that means expected value of b minus beta is 0. This implies expected value of b is equal to beta, and hence ordinary least square estimator is an unbiased estimator of unknown parameter vector beta. Now, in case if you want to find out the covariance matrix, so as I told you, you simply have to find out the expectation of b minus beta into b minus beta transpose. So, now you already have obtained this b minus beta as x transpose x whole inverse x transpose epsilon. So, you simply have to substitute these values over here. So, this will come out to be here like this, epsilon epsilon transpose in the middle part. Simply try to substitute these values over here. Right. Now, I can take this expectation sign inside the bracket. So, x is a non-stochastic matrix. So, the expectation sign inside will be on the random part, which is epsilon epsilon transpose, and you already have assumed actually that expected value of epsilon is 0 and expected value of epsilon epsilon transpose is sigma square I n. Right. So, I can just substitute here this quantity to be here as sigma square here I n, and you can see here that once you do it, you will get here sigma square x transpose x whole inverse. So, this is the covariance matrix of ordinary least square estimator of beta, which is not difficult to obtain. You just need to know the basic matrix theory. Now, there is a concept that when you are trying to find out the covariance matrix, there sometimes people are interested in finding out the variance. So, finding out the variance in case of a vector has a little bit different definition. So, suppose you have got here a covariance matrix, then you know that the diagonal elements, they are the variances, and off diagonal elements, they are the covariances that we know. So, now if you want to find out the variance of B, then this is defined as sum of all the variances, sum of all the variances of B1, B2, Bk. That means variance of B1 plus variance of B2 up to variance of Bk. So, that is equivalent that if you have obtained the covariance matrix, then you can simply take the trace of the covariance matrix. Right. So, the variance of B can be defined as trace of covariance matrix, simply trace of covariance matrix. And this quantity is something like this, summation I goes from 1 to k, expected Bi minus beta I whole square, and this is nothing but the sum of all the variances of Bi, as simple as that. Right. Now, after this we come to the aspect that how are you going to estimate the variance sigma square. This estimation process is similar to the process what we have learnt in the case of simple linear regression model, right? Because you remember that we started with the estimator by guess, and then we converted it into an unbiased estimator. So what we try to do here, that we try to consider the sum of square due to residual, and then we try to take its expectation and try to obtain an unbiased estimator of sigma square, right? So as such, it is difficult to, it is not possible to obtain the value of sigma square as we have found the value of b from by the least square method by minimizing the function s beta. Whereas when we try to do the maximum likelihood estimation, you will see it is possible, right? Okay, so now we try to attempt it, because we know that expected value of epsilon I square is sigma square for all I. So what I can do, that I can use the residuals to estimate the variance sigma square. How? If you remember that we had obtained the residual, say y minus y hat, and which was expressed that y hat is equal to h bar y. So I try to use it here, and I try to use the same concept that I had developed in case of simple linear regression model. I try to consider here a term SS res, that is sum of square due to residual. Sum of squares due to, I can complete this, due to residuals. Okay. And this was defined as summation I goes from 1 to n ei square, which can be written in terms of vectors as E transpose E, and E here you have obtained by here y minus x beta transpose into y minus x b, and which can be using the earlier result what we have just obtained, y minus x b can be written as y transpose I minus h transpose I minus h y, but since I minus h is a symmetric matrix, so this transpose will not make any difference. So I can write down here, and this I minus h is an idempotent matrix, so I can write down finally as y transpose I minus h y, and I minus h is your h bar. So this S sum of square due to residual can be written as y transpose h bar y. And just for your information, there are some other forms also. For example, if you try to write down SS res like this, and if you try to open it, and can you will get this expression also, y transpose y minus b transpose x transpose y, and this expression has been obtained using the normal equation x transpose x b is equal to x transpose y. So this is just for the information that sometime if you use it, or sometime in the book it is given, so you must know that this is an alternative form of sum of square due to residuals. Now I can write down sum of square due to residual as say y transpose h bar y. Now this y is given by x beta plus epsilon, you can say, right, and if you see here, I can show you here, this is the result which I have used here, that SS res equal to this, right. So once I write down here y equal to x beta plus epsilon, then we know one thing here more, that if you try to write down here h bar into x, you can see here I minus x, x transpose x whole inverse x transpose into here x. So if you try to open it, this will be x minus x, x transpose x whole inverse x transpose x. So this becomes here I, and this becomes here x minus x, which becomes here 0. So this h bar x is equal to 0, and using this property I can write down that this that sum of square due to residual can be also written as epsilon transpose h bar epsilon. And now we need to use some distributional properties. So now we are trying to associate the probability density function. So we assume that epsilons are following a multivariate normal distribution with mean vector 0 and covariance matrix sigma square I. So this y will also follow the multivariate normal distribution with mean vector x beta and covariance matrix sigma square I. Why? Because this because y is something like x beta plus epsilon. So you know that expected value of y is equal to x beta plus 0, and covariance matrix of y will be the covariance matrix of x beta, which is 0, plus variance of covariance matrix of epsilon, which is sigma square I. So and y is a linear function of epsilon, which is normally distributed. So, y will also be a normal with the mean vector x beta and covariance matrix sigma square I. And we also know from the properties of quadratic form that y transpose h bar y will follow a chi-square distribution with n minus k. Actually, the rule here is this: y transpose h bar y will follow a chi-square with the degrees of freedom which are trace of h bar. So, trace of h bar you already have found to be n minus k. So, this will follow a chi-square distribution with n minus k degrees of freedom, and we know that once you are trying to take the expectation of a chi-square distributed random variable, then the expectation of this random variable comes out to be same as its degrees of freedom. So, now since y transpose h bar y is following a chi-square distribution and the degree of freedom is n minus k. So, expected value of y transpose h bar y will become n minus k upon sigma square, and if you try to bring this n minus k factor here, then you get here y transpose h bar y upon n minus k. Its expectation is equal to sigma square, and this quantity here y transpose h bar y upon n minus k, this is indicated by ms res. Right, that you will see when we try to conduct the test of hypothesis. Then I will introduce this quantity. Actually, this ms res means mean squares, because I am going to use it. So, I am just introducing it here. So, right. So, this is mean squares due to residuals. Right. So, this comes out to be sigma square, and this sigma square hat now becomes same as ms res, mean square due to residual, which we have denoted by s square. And you will see that when you are trying to implement it in the R software, you will get the value of ms res. So, that is why I am trying to introduce it here. Right. So, hence now if you want to estimate the covariance matrix of y hat, you can simply replace the quantity sigma square by sigma square hat. So, if you remember, we had obtained this covariance matrix of y hat fitted values, which was sigma square say h. Now, I can replace here sigma square by sigma square hat, and I can obtain the estimate of covariance matrix of y hat. And similarly, I can also find out that variance. If you try to see covariance matrix of B is obtained at sigma square x transpose x whole inverse. So, I can replace the sigma square by sigma square hat, and I can obtain the estimate of covariance matrix of B. Right. So, I am just taking this example to show you that what is the use. Okay. So, now after this, let me give you a quick idea about the maximum likelihood estimation. The theory and philosophy behind the maximum likelihood estimation I already had explained you in case of simple linear regression model. So, I am trying to use the same thing, same steps here also. So, now we assume that epsilons are following a multivariate normal distribution with mean vector 0 and covariance matrix sigma square I. This means all epsilon 1, epsilon 2, epsilon n, they are IID, identically and independently distributed following normal distribution with mean 0 and variance sigma square, and hence means I can also find out the distribution of y, which I already have done in the earlier case. Right. So, the probability density function of this epsilon I is given by this quantity 1 upon sigma root 2 pi exponential of minus 1 upon 2 sigma square epsilon I square, and the likelihood function that is obtained as joint density function of epsilon 1, epsilon 2, epsilon n, and since we are assuming that they are independent. So, I can write down them the product of individual f of epsilon i's. So, this is here like this. So, and if you try to write down here, you will get the likelihood function as here like this, summation epsilon I square. Now, if you try to look at this expression summation epsilon I square, summation epsilon square I square can be written as epsilon transpose epsilon. right. So I try to write down it in the form of epsilon transpose epsilon, and now this epsilons can be replaced by y minus x beta. So now this is here the likelihood function. So basically what we have to do, as I discussed earlier, this likelihood function has to be maximized, and then we have to find out the value of beta and sigma square. So instead of maximizing this likelihood function, we maximize the log likelihood. Why do we do it? We had explained it in the earlier lecture that both likelihood function and log of likelihood function, they are the monotonic function. So whatever the solution you are going to obtain by maximizing or minimizing the likelihood function, the same results can be obtained by log likelihood. So I try to take the log on both the side, and I try to write down the log likelihood. And then after this, I simply have to partially differentiate this log likelihood with respect to beta and sigma square. And once you try to differentiate it, which is now very simple, because you can see here, you already had differentiated this function with respect to beta in case of S beta. When you found the least square estimator of beta, you had differentiated the same quantity. So this is the same thing, and now if you try to differentiate it with respect to sigma square, you get here this equation. Now if you try to put these two equations equal to 0, then you get the normal equation, and using those normal equation we can obtain the result. So this is here the same as in the case of ordinary least square estimator. So you can see here, this is x transpose y minus x beta is equal to 0. So this becomes here, say x transpose x beta is equal to x transpose y. So on both the sides you try to pre-multiply by x transpose x whole inverse. So this comes out to be like this, and this implies that beta is equal to x transpose x whole inverse x transpose y, and this is an estimator, and we are trying to denote it by b. Right. So you can see here, this is coming out to be same as ordinary least square estimator. Right. Now you try to take the second normal equation, replace beta by, say here b, or this MLE. Let me denote by here, say beta tilde. Let me try to introduce here the symbol beta tilde just to indicate the maximum likelihood estimator, although ordinary least square estimator of beta and MLE of beta, that is the maximum likelihood estimators of beta, they are the same. So replace this here b by b or beta tilde, and then solve it. You will get sigma square is equal to 1 upon n y minus x beta. The maximum likelihood estimator we are trying to denote by beta tilde and sigma square tilde. So you can see here, this is here like this. Right. And you can see here this part in the numerator, this is the same as OLSE. The only difference is that the term in denominator is different. In the case of MLE, the denominator is n. In the case of ordinary least square estimator of sigma square, it was n minus k. Okay. So now after this, you have obtained these values, and you need to verify whether they are going to give you the maximum or minimum values. So I can obtain the second order derivatives with respect to beta sigma square as well as beta and sigma square, and we can obtain the Hessian matrix of second order partial derivatives, which is obtained here, and one can prove that, which is a negative definite matrix, which indicates that the likelihood function is getting maximized at beta equal to beta tilde and sigma square equal to sigma square tilde. Okay, right. So now if you just try to make a quick comparison, you can see here between the ordinary least square estimation and maximum likelihood estimation, you can see that the ordinary least square estimator and maximum likelihood estimator of beta are the same. Right. So all the properties whatever you have obtained for ordinary least square estimator, they will hold for the case of maximum likelihood estimator of beta also. Like as the case is going to be unbiased estimator, its covariance matrix, estimator covariance matrix, they will remain the same. Right. In case of the estimate of sigma square. The OLSE of sigma square can be found to be an unbiased estimator, because this is the way it has been obtained, right. But the MLE of sigma square, which is sigma tilde square, is not equal to sigma square, and if you try to find out the relationship between the two, it is coming out to be here like this. This is very simple, means right, you can just obtain it here. Sigma square tilde is 1 over n, say SS res, and S square is 1 over n minus k SS res. SS res here is your, so, and then you can simply see here SS res is your y minus xb transpose y minus xb, and you can obtain this relationship from here, right. So, the MLE of sigma square is a biased estimator of sigma square. So, right, now we come to an end to this lecture, and yeah, I agree this lecture was little bit longer, but my idea was very simple. I wanted to give you the complete theoretical structure in a single shot. You have an option that you can watch this video into 2 parts or 3 parts, but my idea was that I wanted to make you confirm or confident that whatever values you have obtained, they are going to give you a good value, and you should be confident that these values have been obtained on the basis of a small sample, but they will be valid for entire population, right. So, my request to you is that you please try to look into this video and try to find and derive the steps what I have given here, whatever I have done here yourself. Unless and until you do this mathematics and algebra yourself with your own hand on your own paper, you will not be feeling confident. So, you do it, and I will see you in the next lecture, and I will continue with the topics on multiple linear regression model. So, see you in the next lecture. Till then, goodbye.